The twin paradox is well known. It has been associated with Einstein's special relativity since day one. And at a certain stage, actually, Einstein himself has been involved in the interpretation or debate about these phenomena. Although many people have discussed these issues, but it would appear that some new perspective can be made if we use the Lorentz transformation properly. Now, this is a twin paradox illustration. In these pictures, we will see that basically they are twins, A and B. A stay on the Earth, while B actually travel with spaceship away and then return after some times. Because the velocity of this spaceship can be very fast, so therefore people say, well, that is a good example where we can apply Einstein's special relativity to dealing with the time, and as well as especially the time dilations problems. There are two twins, and one twin stay A stay on the Earth, another twin B will travel in space, and they will try first move away, and then they will return at opposite velocity. Okay, travel away. So that's why. So the whole journey can be divided into two parts. Now let's consider how to describe this problem. So what we're going to do is that we will first recall the Lorentz transformation. So the Lorentz transformation So if we recall the time in a fixed frame as a t, and then the t prime will be represented the time, local time, where the frame is moving respective with frame A. So that is a t prime will equal to gamma times t minus and v over c squared times x. So where t is the time used by frame A, and x is a coordinate, describes the journey, the distance. To use this formula properly, we have divided the journey into the two parts. One is called away, another is called back. It's very important that when you apply Lorentz transformation, you have to specify that from which is the frame of reference you're choosing. It is important to specify which observer is make such and such claims. So in this case, we just focus on the observer A. So everything we write down here is made by him, by the twin A. So so that is how he would make such analysis and eventually to draw his conclusion. So this is how the observer A would do, and by using Lorentz transformation and eventually draw his conclusion. Now, in the first place, he can argue that the time, you can just copy the time here. So basically, they just use, in this case, because of velocity is positive, it's away. So therefore, you can say the coordinate of the time coordinate, the local time on the frame B can be written as exactly the same as Lorentz formula itself. So where t and x are the time and the position measured by the twin A. This is step one. Step two is that you have to recall that the coordinate x can be simply written as the velocity time his local time, because in this case that the observer A is always uses his own clock. If we substitute this equation into the previous one, so we will obtain that t prime will equal to gamma t minus and v squared time divided by c squared and t. So if we factorize that one, if you factor this one, you will get gamma, and that will be 1 minus v squared divided by c squared times t. Okay, because by definition, this one can be simplified as t over gamma. Okay. So the gamma, I write down here, the gamma by definition is equal to 1 over square root 1 minus v squared divided by c squared. And gamma is also known as the Lorentz factor because it always appears in the Lorentz transformation. So what can we say about that? So basically, the twin A on the Earth can make this claim that he said t will equal to gamma t prime. He can conclude because gamma is larger than 1, so because gamma is larger than 1, so therefore he will just can say, so t will be longer than t prime. So what does that mean is that if they just compare with 2 clocks, and he will certainly say that the process on the moving frame where his twin B used will be slower. The twin B, aging slower in this case. What does that mean is that during the first half of journey, that the twin B does getting younger compared with twin A, who is actually stay on the Earth. But this is just a part of the story. If you want to draw a conclusion at the end of this journey, and then we must have to consider what's going on in the second stage of journey. Now here we can use Lorentz transformation again, but bear in mind, we can use the same notation. We use a t prime to represent the time on the moving frame, or used by his twin B. And the gamma is the same. Gamma factor will be the same, or Lorentz factor will be the same. And time will be the same because the time t will be the same. T is actually his clock. So Lorentz transformation gives people a prediction or judgment based on observer's local time. So this is called the local time. It's called the proper time sometimes. So, but this time you must be careful when the train return to the Earth, the direction of velocity changed. So therefore, here we must use a positive instead of negative. So this is very important because some people would fail to recognize this sign properly. This is step 1. Another thing is that how to describe the position. Another thing is how to describe the position of the twin B on the way back. Now, this is a formula. So basically, if we just starting from counting time from 0, then we can certainly have this formula. So that is a position. We're equal to d minus v times t. So after first journey, after the first journey, we just reset the time so that we can count the time from 0 on the Earth. So if you substitute this equation into this one, into previous one, therefore we can get t prime will equal to gamma. First time, what is the t? Now we are going to replace this by, so basically that will give you x. We have to replace x. So basically let's substitute the x into this formula. We will have the t plus, be careful, t plus. The first term will be v times d. divided by c squared. Second term will be v squared divided by c squared times t, the local time. Okay. So what is a d? So we have to answer what is a d. So by the time, so d can be determined by the time we used. Yes, there's something tricking here. So how about the d? So d can be written as total time spent. That would be fixed. So we have to use the property. So basically total time. Oh, this is something we have to stop because this is tricky here. You write the t, how to replace the t this time? D right there. So d, if we just simply rewrite the d as first half of time, can we just replace t1? So can we just, we know it's t1, it's not t2, so that will be, so basically d will equal to v times t1. So can we call it t1, t2, t1, t2, t times t1 here. So we can write it as v over v squared over c squared t1, okay, minus v squared divided by c squared, d squared, okay. Okay. Now, we missed the t here. Since we are only interested in the total time spent during the trip, therefore, we have to, here we have to, the time taken in the first part of journey is t1 must be equal to the time taken in the second journey. It is important to notice that t1 in this equation is constant, unless we actually just consider the final moment. In the final moment, then we can simply assume that t1 will equal to t2 will equal to t. So t here would be a constant. Okay. What we can obtain is very interesting. So we'll have t prime will equal to gamma times t, because this part will vanished if we just let t1 equal to t. It means that on the way back, the time taken, this is the relation is true. So the t1 is actually, the t prime is actually larger than t. Can you see that? So in other words, compared with the local time, the time on the frame, on the moving frame, the time is getting longer. Which means that this equation, this means that, can you see, the conclusion will be opposite from the first part of journey. And more importantly, which means that in this case, the train B, it will be aging faster. So what does that mean? That there's no such thing or called the paradox. No twin paradox. So the important conclusion here is that there is no such thing called the twin paradox if you use the special relativity property. I hope this reconsideration of the twin paradox will give you some new insight into understanding of Einstein's special relativity, where both time and space are interconnected, interrelated.